All right. So, all right. The other day we talked through this basic idea. What do we do when we're trying to do analysis in the Phasor domain? Right? Circuits don't live in the Phasor domain. There is no such thing as the Phasor domain. It is a mathematical representation of something that happens in the real world. So what you'll hear me, and you'll probably hear Yahoo as well, use this term time domain, which is to say that if I have a circuit, I have a voltage source that's hooked up. The voltage source could be a function generator, could be this thing right here could be the output of your phone, the audio output of your phone or whatever. That's a voltage source, okay? Hooked up to an RC circuit. And in this case, what we said before, I've said this a couple of times, is if I want to be able to solve this thing, I have to do a differential equation, right? That's the only way to figure out the voltages and the currents in that circuit. So what we say is we don't like that. So we move everything into the Phasor domain. We follow these steps where we get impedances and everything. We solve for our phasors, and then we jump back from our result to the time domain. Right? We get, when I say the time domain, what I mean is that in the real world, current is a function of time. All right? And voltage is a function of time. All right? We don't do the analysis in that domain. We do it in the Phasor domain. In the Phasor domain, what are we keeping track of? What are the two things we keep track of in the Phasor domain specifically? What's that? Amplitude and phase angle, right? Because those are the two things we need to know. We need to know the amplitude here, and we need to know the phase angle here. Okay, those are the two things we keep track of. All right, so last time I talked about, and I went through some of the helpful MATLAB commands, okay? So go through that, they're important, all right? So a couple of key ideas that we talked about. We talked about this idea of an equivalent circuit, all right? So basically what I said was VOC REQ here. So I talked about, basically you can have any kind of complicated network you want, right? Like I said, it could be as complicated as the whole North American power system, but I can somehow reduce it to a single voltage source and a single resistor, or single current source and a single resistor. All right, that's the basic idea. And so we said, essentially what I need to know is I need to know what the open circuit voltage is. So I said, basically, I think of any circuit like I got here on the left, right? This circuit is some combination of crazy stuff. That circuit on the left has a set of terminals with a voltage and a current, right? And what we're saying is I can take that circuit, no matter how complicated it is, and reduce it to one voltage source and one resistance, okay? So that resistance there, and this is maybe the key thing, that resistance tells us the effect of what in this circuit, right? What is this guy telling us the effect of? Why is he here? What does he tell us the effect of?
It's the impedance of everything that's in that box.
It's the impedance of everything in that box. And so the reason he affects this voltage, maybe that's the way I should ask the question. The reason he affects the terminal voltage is why?
Because it'll change the current.
Well, because any current that flows changes the voltage, right? So if I go to a wall outlet, like we said the other day, if I go to a wall outlet, I'll measure the open circuit voltage, right? So this middle guy here is my voltage. After I connect a load up, so the top is the current that flows into a toaster, right? After I connect the load up, the voltage drops, and the voltage drops because there's some resistance in there. And this REQ here, right? This REQ is basically representing the combined effect of all of the stuff in the box. All right, that's its job. Important thing is that REQ is the resistance, quote unquote, seen by the load. So what we did the other day is we took an example circuit, this guy here, all right, and we went through and we did the two steps. We found basically what I called the second step, right? We found the equivalent resistance, right? Or in this case, it's not resistance, it's impedance, right? So we went through and found the equivalent impedance. So essentially what we did is this isn't real here, but I drew a current source in because I said the way I think about it is it's the impedance that is seen by the current source, right? When I say seen, what that means is it's the impedance that current will flow through, okay? So we talked about this the other day. When I'm going through this circuit right here to find the ZEQ is looking into, I guess I can't do that. It's looking into these terminals right here. So where do I start the simplification process with this? Do I start near the terminals over here?
Start far from the terminals.
Start far from the terminals. Yes, that's correct. Yeah, I start over here. So let's just to be clear here. So when this circuit, what was my first step?
Turn off the sources.
Well, it's okay. Turn off the sources. So let's assume that's already done, right? What do I do after turning off the sources?
RS and Z1 in parallel.
Yeah, RS and Z1 in parallel, right? So I basically gave you this answer, but I guess what I do is I said RS and Z1 in parallel. So that simplified this circuit here to this circuit here, right? So now I see the ZEQ1 is what? How would I, that guy's in parallel with Z2 or series with Z2?
In series.
In series, right? And they're in series because they share
Same current.
they share the same current. That's the way to say it. Not because they share a node, because they share the same current, right? So then I basically put those guys in series. Then these two are in parallel, right? Why are they in parallel?
Because
see the
they're
Because they share
current.
the same voltage.
They share the same voltage. Yes, that is the way to say it, right? So Z3 in parallel with that ZEQ2. And what I said last time is I have a piece of MATLAB code that I wrote, okay, where I basically went through and I defined all those impedances, Z1, Z2, Z3, right? And, you know, basically what I do is I just define ZEQ1, ZEQ2, ZEQ, basically followed through that whole process. Okay, all right. Now, where we left off last time is basically, we got one other thing, right? So I figured out the equivalent impedance. What else do I have to do to get a Thevenin equivalent?
Be open circuit.
Yep, open circuit voltage, right? So, all right, here's the circuit. How do I figure out VOC?
VOC is the same as the voltage on Z1.
Same as the voltage on Z3. VOC is the voltage at the terminals with no load. It's the open circuit voltage at the terminals. So it's the same as the voltage across Z3. Okay. Now, how should I approach that?
Could do a nodal analysis.
I could do a nodal analysis. All right. I don't like nodal analysis because that means I got lots of equations.
Is
Voltage
Z1
divider.
and Z3 in parallel, right?
Who's in parallel?
Z1 and Z3.
No.
There's a Z2 between.
Okay. Yeah. Let me. Yeah. So a couple of observations there. So a couple of things that are not wrong that people said. I could use nodal, right? If I've got nodal, how many nodes do I have to solve for here?
2.
One,
Oh, yeah.
right? There's only one node to solve for here. Which one is it? Where is it?
D1 and Z2.
This guy here. It would be this. All right. If I did mesh, how many do I have to solve? How many meshes would I have?
2.
Two. All right. When a circuit is this simple, right? If you like to do mesh, great, good for you. That's okay, right? I wouldn't want to do mesh, right? Because I don't like solving multiple equations, and mesh is messy, in my opinion. I know you guys are much more comfortable with mesh and nodal. I get it, right? But you need to be able to handle all the different approaches. So let's take mesh and nodal off the table, okay? In this case, what should I do? I heard somebody say, are Z1 and Z3 in parallel? They're not, right? There is a parallel combination here that I can look at, right? So Z1 is in parallel with something, isn't it?
With VS.
What? Yeah, what's Z1 in parallel with?
VS.
Z2,
2 and Z3 are in series.
RS and VS.
Yeah, so I heard somebody say, yeah, it's in parallel with VSRS. It is in parallel with that series combination, but that's not really helpful for me in trying to be able to simplify the circuit down. What is clear here, right, is that Z1 is in parallel with the combination of Z2 plus Z3. You guys see why that is? Why is that?
I have a question. Is that because on the right side, basically since it's an open circuit, like there's no current going out of it, like
Yeah,
Because
when this,
yeah,
yeah, when
Oh,
this
yeah.
is open circuit, there's no current here, right? So those terminals sometimes throw people off, seeing those terminals. You know, well, there's something there. There's nothing here right now. It's open circuited, right? So Z2 and Z3 are in series because there's nothing out here for current to flow into at that point. Okay, so it's an open circuit over there. So why is Z1 in parallel with the combination Z2 plus Z3?
They share the same voltage.
They share the same voltage. Yeah, they got the same voltage across them, right? Okay, so so that is that. So I would use that right there to say this circuit then comes down to VS, which is a phasor. So I write it with that bar under it. Here's RS. And then I would say there's some, I think in my code here, I called it ZEQ4 because it's complicated, right? So ZEQ4 is this, right? You see what I've done there?
Yeah.
Okay. So what's that going to tell me? That's going to tell me the voltage here, right? I want to call that V, I guess.
So to get that voltage across Z1, you need to make RE like ZEQ for the whole other side. We can't just do a simple voltage divider for that V.
What would your voltage divider that you're proposing include?
Wouldn't it just be VS over RS plus Z1 times Z1?
I'm really glad you asked that because that's what a lot of people say. That doesn't work. And that doesn't work because what's required to have a voltage divider? What? They have to be in series, right? So this is why I talked about this the other day. This is a great question because I think a lot of people have that question. So the voltage divider, I said that rather than remembering the formula for it, the key thing is to remember why it's a voltage divider. So the key idea of a voltage divider, it applies in these conditions when the items are in series. In other words, when the current through them is the same, right? So I need to know the voltage across the series, right? But the key thing is this only applies when the current through the devices is the same. So if I look at a circuit like this one, right? Could the current in RS and Z1 be the same?
No,
No, because it's got a split.
Mhm.
Right? So I don't have a voltage divider. However, I would say that Z2 and Z3 are a voltage divider, aren't they?
Yeah.
Yeah. So I can say if I know what V is, so V, the voltage I defined across Z1 right here, right? If I know what that is, I can say that VOC, that phasor, is equal. How does that relate to V, this voltage across Z1?
V times Z3 over Z2 plus
Yep.
Z3.
Yeah, exactly. Right, that. Okay. Now, you guys like to get to numbers. I like this. I actually prefer what I've written here on the screen. So for instance, you won't see that so much on this test, but on exam 3, when it's all going to be about this stuff, I'm going to be probably asking you for this kind of symbolic stuff. Because to be honest with you, so understanding these equations, this is where you're showing you understand the physics. When we grade your exams, you can ask Amber this. She's grading some of your exam right now. There's 115 of you guys. I guarantee you 100 of you are wrong on your numbers, right? And that's always going to happen. And it's not to say that you were wrong on your physics, right? Where you get partial credit is when you're right on these equations, right? So I'm not as concerned about the numbers. I'm much more concerned. You'll see me ask a lot of questions about set up the equations. If you're good at circuits, then you're good at setting up the equations. With all the many steps of the math here, you're going to screw up, right? Especially under time pressure. I know that. All right. So I'm not worried about the math. I'm worried about the physics because it's the physics that you're learning here. You guys learned arithmetic a long time ago. All right. And there's a lot of steps of arithmetic, a lot of places to make mistakes. So in other words, you'll see me write a lot of stuff like this because this is where we do the learning, in my opinion. All right. So a long-winded professorial way of saying, okay, here's how I get VOC. The thing is, I haven't said what V is yet, have I? How do I figure out that V?
The voltage across that parallel combination.
The voltage across that parallel combination. Yeah, so, and it looks like in the circuit that I have right here, this is a voltage divider here, right? So I could say that this V is equal to what?
Vs over Rs plus ZEQ4 times ZEQ4.
Yes. And again, let me write that the way that I think of it is voltage divider is basically I got to get the current first. So Vs, I write it in a specific order, Rs plus ZEQ4, right? That's the current. I multiply that by ZEQ4 to get the voltage. So if I wanted to solve this thing, you look at what I do is I basically do this, and then I do this, right? So I do it in steps like that. I like this because there's lots of things I can see about this that I like, right? I can see when I look at this equation that I have volts divided by ohms, which is amps. I have amps times ohms, so I have volts.
So
I can
for-
check that my answers make sense, right?
For us to use then like those series and parallel relationships for current divider and voltage divider, do they have to be the same circuit elements? Like Vs and Z1 are in parallel. So could I do a current divider there since they're in parallel? Or I can't because
You
it's a-
could. So Z1 is in parallel with Z2 plus Z3, right? We said that. So if I know the current entering at this node right here, then I could do a current divider.
Okay.
But I would need to know that current first, which means that I would basically have to still analyze this circuit to figure out that current, right?
Excuse
So-
me, Professor.
Yeah.
I have a question from what we did last time. So last time you did a source transformation on VS. So after you did that source transformation, could you just do a current divider from the 3 branches, and then whatever you get for
Yeah.
that third branch, you could use to find VOC?
Yeah, so you could do that too. So basically, if you look at this circuit, let me. Yeah, there's many ways to skin the cat here. So yeah, I think what I started doing last time is I said, well, I could do a source transformation, which is basically to say I'm making a Norton equivalent for some other circuit, right? So I'm saying this guy becomes Vs over Rs. This is Rs. Yeah, and I think this is actually how I wrote my code. And then I've got Z2 and Z3 in parallel. And actually, this is a good exercise to go through. This guy, I would use a current divider here. Right. Like that. Right. So if you look at that arrangement, right, the way I could find VOC, here's VOC. There's a couple of ways to do this. I could do a current divider here. I could do, so let's say I wanted to use a current divider. How would I do the current divider approach?
So it would be
So think about, so current divider, how would I apply that here?
V over R used to be.
Okay, so the first thing is to be able to do a current divider. I've got how many things in parallel here?
3.
3. All right, 3. So the first thing I got to do is I say, well, I know the current going in, that's this IS. I want to figure out the current in which branch?
Z1.
Not Z1.
Z2 and Z3.
Yeah, if I'm trying to get VOC, I mean, there's nothing wrong with getting Z1, but I want to get the current over here. I'll call it I3, I guess. Okay, I want to get that current. So if I want to get that current, what do I need to do to get that current?
I'd start by converting Z2 and Z3 into an equivalent impedance.
There's, so I could combine Z2 and Z3 into a series, right? But if I want to think of the way I think of the current dividers, if I want to get a current in that branch, if I want to get I3 there, the current in that branch is always equal to what over what?
the voltage over the
Divided by the
resistance.
equivalent resistance.
Yeah, the voltage divided by whatever the resistance in that branch is, like that, right? And so I think that voltage is basically the same voltage we're talking about here, isn't it?
Yeah.
Okay. So how would I figure out that voltage? What's V? Oh, what's V?
IS times RS.
Nope. So it's the voltage across the parallel combination of RS, Z1, and Z2 plus Z3 in series, right? So it's the same thing as before. It's going to be V is IS, the current entering this parallel combination over here, right? The current entering that combination, which is IS, times that parallel combination. So in this case, that impedance of that whole thing is going to be 1 over RS plus 1 over Z1 plus 1 over Z2 plus Z3. I take this result, plop it into there. I get the current in that branch, right? The current in that branch, so VOC would be I3 times Z3, like that, right? That's another way to do it. There's lots of ways to do that. You guys are asking good questions about it, right? Important thing is forget formulas, all right? I keep saying it, forget formulas, right? Just it all comes down to KCL, KVL, and Ohm's law, right? And remembering these basic principles, okay? Any other questions before I move on from this one? All right, real quick, there's one step we also said, right? So once I get a phasor for VOC, right? At the end of this, I'm going to get a phasor for VOC. We said that doesn't exist in the real world, right? There is no phasor in the real world. What exists in the real world is VOC of T, right? How does VOC of T relate to the phasor of VOC? It's going to be a cosine, right? And what's in front of the cosine?
Amplitude.
Amplitude, and it's going to be the magnitude of the phasor, right? Times cosine of omega t plus the angle. So let's see. Back at the beginning of the problem, we were told that the frequency was 10 to the 5th radians per second. The frequency never changes, right? So I'm going to make this guy, whoa, come back on me. 10 to the 5th t. And then what do I add to that?
The phase.
Yep. So I say the angle of VOC, whatever that is, like that. That's my final expression. So, and what I did the other day, what I did was I did my source transformation, went through that whole process, right? And then here's me going through that whole thing there. So if I do this and I run this code here, let me just run this code. Uh-oh, didn't like me running that code. Why not? Uh-oh. Let me do this. All right. Yes. All right, so what did I get at the end? VOC. It didn't run that far. All right. That's what happens when I test this all of a sudden. All right, let's see. So there we go. All right. So I got VOC is this guy right here. So we said if I want to figure out what the magnitude of that is, I say abs of VOC, like that. So I find out this guy is 7.62 volts. Okay. And the angle of that is, now if I type angle of VOC, we talked about this the other day, what's the units going to be when I type that?
Radians.
Radians, right? So I want to convert that to degrees. So I'm going to say deg to rad.
What did you need rad today?
Rad to deg. Yes. I usually just multiply by 180 over pi, but yes, I did mean that. All right. So negative 31.569 degrees. So that says 7.62, negative 31.56. So I would say the amplitude here is 7.62, and this is negative 31.6 degrees. Okay. All right, questions about that? Many, I suspect. Too many to ask. Okay. All right. We're going to talk, we have all week next week, we're going to have more fun with circuits. Okay. So we'll deal with this stuff later. Get out of my way. I want to go and start talking about the other stuff. All right. So today I want to talk about nodal analysis. Now, everything I said, like the other day, nodal analysis, mesh analysis, all of it, it's all the same, just with phasors now. All right. That's the only thing that's changed. Nothing else has changed. Okay. All right, so basically I wanted to launch into this piece because I've said it and I wanted to write it down and put it in the notes formally. Circuit analysis is just that, all right? And you probably like, oh yeah, he's being a jerk. He says the rest is just details, but these are the important points. KVL, KCL, the key relationships. And this line here is important. These things I call constituent relations. What they do is they tell me how voltage and current relate in a given device. So if I have a resistor, if I have an impedance, voltage and current are related. Okay, and then I need to use the passive sign convention to determine the sign of that voltage. What's the passive sign convention again? What does it tell me?
The flow.
Here's Z, okay? I got an impedance. If I define the voltage this way, and I define the current this way, into the plus terminal, what's the relationship there?
It'll be negative.
Nope,
Positive.
positive.
Passive sign convention.
Right? That's important. If I took that that current and I reversed it,
Then it would be negative.
then it would be negative. All right? That's all it comes down to. All right? Is that. And these are the things that we really need to remember. All right? Because it all comes down to that. All right? And I think people forget this part when they start doing mesh and nodal analysis, and that's where the mistakes start coming in. Okay, so we're gonna deal with some of those things. Now, I added these other 2 points because they're really important as well. The voltage across a current source is defined by the circuit. In other words, there is no relationship in a voltage source or in a current source. There is no relationship between voltage and current. Okay, the voltage across a current source is defined by the circuit. Okay. The current through a voltage source is defined by the circuit. You have no mathematical way to relate those. If I have a resistor, and I know the current, I know the voltage. Okay. If I know the current, I know the voltage. If I know the voltage, I know the current. They're related to each other. In a voltage source, I know the voltage. That's it. I don't know the current, right? Example of that, if I take a car battery, right? I have a car battery sitting there. How much current is coming out of that battery? None. There's nothing hooked up to it, right? So zero current comes out of that battery. Now what happens, don't do this, but if I take a wrench and drop a wrench across that thing, all right?
Day.
Bad day, yeah, definitely, right? How much current's gonna come out of that guy?
A lot.
Infinite.
A lot. Basically, in theory, if that wire has, so give me a model for that thing, okay? So the battery is here. All right, this guy's a voltage source. Let's make him 12 volts, right? What have I done?
You
A
put a
short-
well, yeah.
Yeah. So the theory says, how much current do I have here?
Infinite.
Infinite. Yeah. Infinite. Yeah. I mean, in theory, I got infinite there. Now, it's not going to happen that way, right? Because there's got to be some resistance to the wire, but it's small. So what's going to happen is there's going to be an explosion of fire, or there's going to be some bad stuff, right? That happens there. But if I put nothing on the battery, it does nothing. It's safe, right? There's no current comes out. If I put a wrench across the terminals, then it's dangerous, and it gives me whatever current I ask for. If I ask for nothing, it gives me nothing. If I ask for everything, it gives me everything. If I ask for something in between by doing something reasonable and putting a resistor on here, then it gives me something reasonable. Okay. All right. Now that's the way I think about it. Now, by comparison, there is such a thing as a current source, because you can think of a battery. You've known batteries since you were a kid, right? You could think of a battery, right? That's a voltage source. Current source, those are real things too, but it turns out you can't go to the store and buy a current source. Like I can't go to Home Depot and buy a 12-pack of current sources. Like I can buy a 12-pack of batteries, right? Example of this would be if I hooked up so PV panels, solar panels to the grid, right? This guy is okay, there's a bunch of solar panels, and then there's this thing called an inverter that hooks it up to the grid. The grid, how would you model? So I've talked about this kind of before. What would be from a circuit, if I looked at the wall outlet, right? Going into the wall outlet, what does it look like? What's the circuit model? I can make a Thevenin equivalent for it, right?
Yeah.
Right? And so there's going to be a VOC, right? And there's going to be an impedance, ZEQ, okay? That's the grid right there. Grid's complicated, very complicated place, but it can be made that simple, okay? What do you think this inverter looks like? If I had to make a model for all this stuff over here, what would be a model for it?
It's also just going to be a voltage source.
You would think. It turns out that it's a current source that it looks like. So it can be turned into a current source, okay? If I had a current source and I took a current source and short-circuited that, does that sound like a bad thing?
There's no voltage across it.
There's no voltage across it. But I mean, I think most of you guys know, even if you've never done it before, you know that the picture I drew there is a bad thing, right? I shouldn't put a wrench across the terminals of my car battery, right? But is this bad? If I had a current source and put a short circuit on that, is that bad?
No voltage.
No voltage. Yeah, it's no voltage.
It has a steady amount of current, so it shouldn't be a problem.
Exactly. All right. If I take a PV panel and I take the two leads and short circuit them, it's fine. It gives me, if this guy is 8 amps, I get 8 amps flowing over here. And how much voltage do I get? Zero. And no power. Right? Actually, the thing that's bad is if I did this. If I opened it, how much voltage do I have then? This guy is infinite impedance, right? So how much voltage do I have? An infinite amount of voltage, right? So you don't want to do that. Okay. All right.
Then if you open it a voltage, it would only have that.
Yeah, opening a voltage source is fine, right? Right. It's just because it has no current, right? Shorting a current source is fine. Okay. Now I say that because to mean that, in this case, in a case of a battery, the circuit, in this case, this R, determined the current. In case of a current source, the R I connect determines the voltage. Okay. That's an important point. And I make that point because we're going to use it here right off the bat when we get in mesh and nodal analysis. Okay. All right. So I want to talk about something because I do, the way that I learned, and I think probably most of us learned the node voltage method, is a little bit different than the way Zybooks does it. However, what I do and what Zybooks does is entirely equivalent. All right. So I want to show that to you. Right. So if I'm given this, all right, if I've got a circuit like what I've shown right here, the idea of nodal analysis basically is what? When I'm doing nodal analysis, what am I doing? I'm doing KCLs, right? I'm doing KCL equations to solve for what? Not to solve for current.
The voltage.
Call for the
The
voltage.
voltage.
I'm solving for voltages. Yeah. So in general, what we say is that that in any circuit, it has n independent nodes. So in this case, how many independent nodes are there that I actually have?
Does the ground count?
Well, it does technically, right? So what we do is we call this guy ground down here. All right. And we say that he is equal to 0 volts.
That would be 3 nodes then? Counting ground?
Yeah, 3 counting the ground. So there's one up here. I'm going to call this guy V1 and call this guy V2. Right? Technically, I guess there's one here too, but it's known to me here, right? Okay. I'm never going to ask you a question, how many nodes are there in this circuit, right? But it's important that we understand that we're solving for these voltages. Now I ask you this question, here's a practical question. Where does this come from, 0 volts?
It's a reference node, no?
It's a reference node, but okay, you know, if you go to your wall outlet, it has a ground. Why is it called that?
Ground is just arbitrary so that you can figure out how much voltage is higher than it. So say like you have,
Yeah.
say you have a voltage source coming down at the bottom, you could also have it attached to the same reference, and then you'd have it where it's only up the amount of voltage it is. And then you wouldn't have to do as many calculations.
Okay. So Mikey, you were very passionate in your response there. That was good. Yes, it's a reference, right? It was a very thorough response. I liked it. So in practice though, like, so just to be clear, so yes, it's a reference. You choose a node to be a reference, right? Why do we use the term ground? Anybody know?
Why isn't it connected to like if you follow that wire, isn't there like a big rod that goes into the ground?
Yeah. So
It's
if you go to
connected
your, if you go to your house, right, what they do is they will drive a rod into the ground, right, for the negative terminal, right? So coming into your house is basically a voltage that is AC, right? And the negative terminal of that voltage is driven directly into the dirt. All right. So, and that dirt is referenced, is the reference node. It's called 0 volts. We call it ground because it's literally in the ground. Okay. And that's why we use that terminology.
I have a question.
Yeah.
Why is that they drive it to the ground? Is it to?
So yeah, you need to have a reference. And so in other words, voltage is always measured with respect to 2 points, right? And so what we do is by driving that rod into the ground, we basically, we know that the earth is a safe place, right? It's not electrically dangerous to us. By making sure that I connect the negative of the circuit to ground, I know that the negative is connected to a safe value, okay? And we'll talk about this a little bit when we get to power, right? Later on in the semester. But when I connect to the ground, I know that I have a safe point. If I didn't have that and I didn't connect this system to ground, this guy could be many thousands of volts above the ground, which we know to be safe, right? And that could be dangerous. All right. That's a problem we'll talk about a little bit more when we get to power. For right now, the important thing is not even to call it ground. It's really our reference node, right? We've defined that it's 0, and then everything else is going to be defined with respect to that. All right. We'll talk more about the details of that later. Okay. But the important thing is each node has a voltage with respect to ground, with respect to the reference node. Okay. We write a set of KCL equations, meaning we write current equations to solve for voltages. All right. We're solving for voltages using currents. Okay. All right. Now this gets tricky when I get things like voltage sources in between nodes. Right. So that's where it gets a little bit tricky. All right, now a couple of things here. Voltage is always, the way I do this is basically in a couple of steps. If I'm writing KCLs, what I do is I define currents like I have right here. All right, so this was my node 1, call that V1, call this V2 like that, okay? All right, now, if I'm gonna write my equations, I don't start them the same way that you guys do, which is to start writing equations in terms of voltages. What I'm gonna do is I'm gonna write them first in terms of currents here. Right, now I know this is not the way that you guys did it, but I'm going to do it the way I did it. All right. And then I'm going to try to relate it to the way that it's in Zybooks. So if I've got this guy here, I don't even think about the node voltages right now. Okay. What I'm going to do is I'm going to call this here. Boy, what am I going to call it? I'll call this VA. I'm going to call this VB. I'll call this VC. And I guess I'll call this VD, okay? And I like doing it that way. So I'm gonna say VA is the voltage across R2 plus R3, all right? VA is equal to a current times a resistance, right? VA is what in this case? How would I write that?
Times R2 plus R3?
Yep, I2 times R2 plus R3. Okay. And that voltage, VA, can be written in terms of the node voltages. So how would I write that voltage in terms of the node voltages? Yep, V0 minus V1. Okay.
Oh,
So that's how I figure out what I2 is. I2 is equal to V0 minus V1 divided by R2 plus R3. Okay. And then I do VB. How would I write VB? Well, it is V1.
I3 times R1.
Yeah, V1 minus 0. Yeah, and it's I3. I heard somebody say that. I3 times R1. Okay. Like that. All right. So now I've got my other equation here. I3 equals V1 over R1, like that. Okay. Then I could do the same thing for VC. VC is equal to what times what?
I4 times R4.
I4 times R4, which is equal to, how do I define the node voltages there?
2 minus
V1
V1.
minus V2.
V1 minus V2, and this is important. It's V1 minus V2 because it's the voltage at the plus terminal minus the voltage at the negative terminal.
Like higher to low?
Always
High
high to low.
potential.
Yep.
Yeah.
The important thing is when it comes to signs on this stuff, you're never wrong. There's no wrong answer when it comes to signs. You just need to be consistent with the signs that you chose. Okay. All right. And then I chose some other, I had this guy VD, right? So VD is going to be I5 times R5. And in terms of the node voltages, what is that guy?
V2 over
V2 minus 0. Okay. Now, again, why do I like to do stuff? Like a couple of reasons. I like to look at these equations because I can see that I get unit consistency, right? Looking at problem 4 on first exam, a lot of you guys are going to be unhappy because what you're going to see is you got equations you wrote down that are just make physical nonsense. You have currents with terms in volts and amps in the same equation. Doesn't make any sense. Okay. All right. So it's really important to me to look at these equations like this. All right. Now I do this, and then basically what I say is if I look at this picture here, what I do is I write my KCL. So at node 1, what's my KCL?
I2 equals I3 plus I4.
Yeah, I2. I always do it current in equals current out. So I2 equals I3 plus I4, like that. All right. And then I can similarly do node 2. Node 2 will be what? Yeah, how do I do node 2 here?
I4 plus
I4
equals I5.
I4 plus I0 equals I5. Okay. And then I can go in and I can replace in those equations that I just wrote down on the previous slide. All right, which are going to be, if I go back and do them, and you can watch it slowly later, V0 minus V1 over R2 plus R3 equals V1 over R1 plus V1 minus V2 over R4. And this guy is going to be V1 minus V2 over R4 plus I0 equals V2 over I5 or R5. All right, now quick check, all those equations. What should be the unit on every term in those equations? Amps, right? Every term there has units of amps. So if I see voltage over ohms, right? V over R, that's got units of amps. Every term in your KCL equations better be in units of amps. Okay. So lots of them on the first exam that are not. Okay. So every term better be in units of amps. Now, the Zybooks approach it works, but I don't like it. All right. And the reason I don't like it is this guy right here. Okay. I don't like that. Because there's only one way current's going in that device. I don't care which one you choose. All right. I don't care which one you choose. All right. But I just don't like that. All right. Now, if you're comfortable with that, fine, because you're gonna get the same answer that I got. Now in the Zybooks approach, if I do this at node 1, what would I say at node 1? Yeah, so if I do this at node 1 and I use this picture right here, what would be the KCL I would write in terms of the currents?
V1 minus V0 over R2 plus R3.
Okay, so start just with the currents that are defined there. Don't start putting in terms of the node voltages yet.
I1 plus I2 plus I3 is 0.
Yep, I1 plus I2 plus I3 is 0. Okay. And then at node 2, I'd have a similar equation, right? At node 2, I guess I'll do it over on this slide. Node 2, I will have what?
2 minus
The
V1
sum
over
of the.
R4.
Yep, I4 plus I5 plus I6 equals 0, right? The currents always go out, okay? Now, what they do, whenever I do this, they're making an assumption about the directions of the voltages on top of the resistors, right? So you always, how do you write the node voltages for each of those currents then, when you do it this way? Let's say for I2, how would I write that?
V1 minus VO over R.
V1 minus VO, yeah. So I would do it basically in terms of the node I'm leaving from to the node I'm going to, okay? So I get V1 minus V0 over R2 plus R3. All right, what would I get for, so this was I2, I guess I should be clear, but this is I2, right? Plus, now let's do what they call I1 here. So what would that be?
V1 over R1.
V1, the node I'm leaving from, minus 0, the node I'm going to, over R1. And I3 would be what?
V1 minus V2 over R4.
Over R4 equals 0. Now that is the equation I got for this guy. If you compare that to the equation I got doing it this way, which again is a lot more traditional to write it this way, all right? Because there's no, in other words, it just requires me to know Ohm's law and KCL, right? This is more traditional to do it this way. This uses a trick. You're basically, the node you're leaving to the node you're going to thing is a trick that's kind of simplifying the passive sign convention a little bit, okay? Nothing wrong with it per se, right? It works. If you look at this equation here, and you look at this equation here, they are the same equation. The only thing that's different is I would need to take this term over here and bring it over to the other side, right? So if I brought this term over to the other side, I would have exactly this equation, all right? So if you see it written out on the test my way, and you don't want to do it that way, fine. Do it your way, and you'll get the same answer. If you're right, I'll give you the correct answers, right? And we've done that on the first exam, okay? Now, on an exam, I'll often tell you to do it this way, right? The reason I'll tell you to do it, I don't care if V1 is 4 volts and V2 is 6 volts. I don't care, right? That number means nothing to me, right? What means everything to me is that you can look at that equation and recognize that that equation is consistent with the basic physics, okay? This isn't a math class. It may feel like a math class. It's not a math class, right? We're learning how to write the equations. That's what's important to me. Not that you can solve them, that you can write them.
So we could just write all the equations and then use MATLAB to get our answer and put the answer in exam.
So this is the thing you guys are gonna have trouble wrapping your head around. On an exam, I might not even tell you to give me an answer, right? Like on exam 1, if you look at problem 4 on exam 1, I didn't ask you to solve any of the node voltages. I just wanted their equations. And I know it's weird to you guys because your brain is like, what's the number? I don't care about the number, right? Now, sometimes I will tell you I want a number. Like for all the second order stuff that you're doing, you obviously have to write numbers for that, right? It would just be ugly equations. But this, when I look at this, it tells me I know the physics, right? And a lot of the things that I saw on exam 1, and you guys will see it beginning of next week, is you have equations where if I look at this guy here, he's got amps, right? I'd see equations where then the next term would be in volts. And that tells me you don't know how to write the equations. Okay. So, if I do ask you for numbers, then yeah, Zach, what you asked is exactly what I would allow, right? You get these equations, then put it into matrix form and solve it, right? That would be perfectly fine. But oftentimes I'm not going to ask for numbers, right? On an exam, I wouldn't ask for numbers. I want to see this. Because honestly, like I said, your numbers are 9 times out of 10, your numbers are wrong, right? So why ask you to go 20 steps when I only want to see step 1? Okay, that's part of the logic that I use. All right. Questions about that? All right. Let's look at where this gets hard. All right, where this gets hard is the idea of a supernode. Okay. Now, why does this get hard at a supernode? So let me do it. I'm going to do this my way here. I'm going to call this I1. I'll call this I2. Call this I3. I'll call that I4. I've just defined them in ins and outs. Now, and let's say this, I don't know, this picture I stole from, let's say this was ground right here. Okay. Right there. So you could define currents. I2 you could define right there, right? You can say that I2 is equal to what? V2 R3, right? You could totally say that. You can do something similar for I3. All right, what about that voltage source?
You don't know the current through it.
You don't know how to relate it.
Yeah.
Right? What do I know?
Didn't you say V3 minus V2 equals 10 volts?
Well, I can certainly say V3, yeah. So one thing I definitely know is the voltage difference between those two nodes, V3 minus V2, has to be 10 volts because I stuck a voltage source. In other words, I forced, and where did that come from, that statement? Just to understand where that statement came from. Well, that's KVL, isn't it? KVL around a loop right here. Right? This guy is V2 with respect to ground. This guy is V3 with respect to ground. If I do a KVL around that loop, that statement results. Okay. V3 minus V2 is 10 volts. Okay. Just a KVL statement. Okay. What about the current in here, though? I mean, this guy has a name. Let's call it I5. Okay. There's a current there. How can I figure out I5?
If you determine I1 and I2.
That wouldn't, okay. Let's look at it this way, right? Here's the way I look at this. I don't have, there's no constituent relationship. We said, if I know the voltage across the set of nodes, and if I have a voltage source, I have no way to define the current. The circuit tells me, right? So in this case, what would I say? I would say at the V2 node here, all right, what I would write is, I would say KCL is I1 enters, and what's the current leaving? I2.
I2 and I5.
Yep, I2 plus I5. Now at the V3 node, what's going on there?
I5 is coming in, I4 and I3 are leaving.
Yep, I5 enters, and then I4 and I3 are leaving. So what can I do? I can combine those two things, can't I? Yep. So check this out when I combine those things here. So what's it say? It says, if I look at this, it says I1, the current entering here, all the way over here, that current equals the current going here, and then plus the current going here, but the current going here is the same as the current that leaves at the other side, right? So basically what you're saying is I can think of this thing with this picture. Just imagine the voltage source isn't there and these guys were kind of sort of connected to each other, right? And you say, well, here's I1, here's I2, here's I3, here's I4, like that, right? So whatever, so you could kind of think of this node being pulled, the V3 node being pulled over to there, right? So whatever's entering at I1, in this case, I would have I1 equals I2 plus I3 plus I4, right? This is the way to really think of it here, right? Whatever current goes into this voltage source here comes out of it over here, right? So there's a current going in on this side, the left, and there's a current going out on the right. Okay. So it says, all right, that voltage source controls nothing about the current there. So just pretend like it's not there. All right. And then I need to add this other constraint, which is that V3 minus V2 is equal to, in this case, in my example here, 10 volts. Okay. You guys follow that?
Yes.
All right. A lot of people did not follow that on the first exam. I know that. All right. All right. That's this. And this is one of the most confusing points in circuit analysis, but it's also an important one. Right? If you understand this, then you understand it all. All right. This is where weird stuff starts happening in general, because I'll see people write things like I1 plus I2 equals 10 volts. Right. That voltage source really throws you off. Okay. The important thing is, from the analysis of the currents, it's as if that voltage source isn't there, right? Because it doesn't control anything about what the currents do. All right, so we're going to do that to analyze this particular circuit right here, okay? So I want to look at this guy here. So for what I have right here, it sure does look like this guy is a little bit complicated, doesn't it? So if I want to do nodal analysis here, all right, so this guy starts with my usual approach. So first of all, when I want to solve for this in the Phasor domain, okay? So do I have a super node here?
Oh, you have a super node?
Yeah, I totally do, right? I got a
Oh, yeah,
super
you do on
node
the
there
top.
in the middle. Now, before I can even get started with this, am I in the Phasor domain with the picture I have there?
No.
No, I'm not. What's the first step to get into the Phasor domain?
Converting the
sources
inductor into
to phasors.
capacitors.
Go to phasors, right? Go to phasors. So look at this. I can go to phasors. I'm gonna say that this guy up here was what did I gave it a name. I called it VS. Okay. And then I've got, let's see, I've got a resistor here, a resistor here, and a capacitor here. And I had a current source here, which I called IS. Okay. And then over here, I had an inductor and a resistor. All right, R and L. And VS, if I look at that previous slide, VS is 6 cosine 100t minus 30 degrees. So what's the phasor for that guy?
6 angle negative 30.
Yep, 6 angle negative 30. 6 angle negative 30. Okay. And for IS, it is what?
2 angle.
2 angle 0.
2 angle 0. I was going to say 2. Okay. All right. Now, then the inductor has an impedance. All right, here's C. The inductor has an impedance, ZL. What's the equation for that?
J omega L.
J omega L. Okay, and I can just plug in. And what do I use for omega here?
100.
100t.
100. Okay, omega is 100. What are the units on that guy?
Radians per second.
Radians per second. Okay. All right, so I'd plug that in. Now what about the capacitor? What's his impedance here?
1 over J omega C.
1 over J omega C, and then the resistor is just R, right? Now, if you look at the numbers that I'm using in this particular case, all my R's are 1 ohm, okay? And I have 10 millihenries and 10 millifarads, okay? And I am going to call this bottom node ground here. I'm going to call this guy here V2. I'm going to call this guy here V1. Okay, now to do this problem, how am I going to approach this? Well, what I'm going to do is I'm going to call this current here I1. Okay, I'm going to call this current here I3. I'm going to call this current here I4. Like that. Okay. Now, how should I approach this? All right, in terms of the way that I like to approach this, all right, how many nodes do I need to write a KCL for here? Just one.
Super.
Oh, yeah, correct. The supernode.
Got a supernode going on.
Does
right?
it matter that it's the voltage source?
I'm not sure what you mean by that.
Well, in the last one you said in the last example, you were talking about how we can just remove that supernode voltage.
Yep.
But since this is the voltage source for the circuit, would it matter, or is it all true?
Oh, it's still true.
Okay.
There's another source in that circuit.
Yeah.
Right? There's two sources of energy here. One of them is coming from a current source. One of them is from a voltage source. I got two energy sources going on here. So I look at this guy, and my analysis of this is basically the same sort of thing, right? I can, again, sort of think of this guy as just not being there for a second, right? That's the easiest way to do it. In other words, you could pull V1 and V2 together. It's not true, right? But I could think of it that way. So if I do it that way, how, in terms of what I wrote there, I1, IS, I3, I4, what would be that KCL relationship here?
IS equals I1 plus I3 plus I4.
Exactly. IS equals I1 plus I3 plus I4. Okay. All right. That's the only KCL I can turns out that I can write. Again, that's the easiest way to do it. Erase that voltage source in your mind, right? That way, you know, if you think about it, then I could technically redraw the circuit with this guy, this V2 pulled all the way over to V1. It's not true, right? But I can think of it that way for the reasons that we said over here, right? That the current that enters on the left side leaves on the right. Okay. So back to my picture here, the voltage source VS comes back into play right there. All right. So I can only write one KCL. I need another constraint because I got two nodes. If I have two nodes, I need two equations. What's the other equation here?
V1 minus V2 equals VS.
V1 minus V2 equals VS. And that is a statement of KVL. All right. So, all right, now I got to figure this out. IS over here is equal to I1 plus I3 plus I4. All right, so again, I got to write this as the volt. So I1, how do I define I1 in this case? What over what?
What would be
V1 over impedance.
Okay, V1 over V1 minus 0 over R plus ZL. Okay. For I3, what would that be?
V2 over R.
Over R.
V2 over R. And what's I4?
V2 over R. Then ZC.
R plus ZC. Yep. Now, and I'll put minus 0 because it's always minus another one, right? In this case, it's just minus 0, so it's going to simplify out. All right, so at this point, I have, for myself, I basically have two equations and two unknowns. What I do is I put that into MATLAB, right? So I would rearrange this guy and put it into MATLAB. So one of the equations is basically V1 minus V2 equal to VS. VS, I know what that is, right? That was, what was it? 6 angle negative 30. Like that. The other equation I've got is this ugly guy here. All right, so I'm going to try to write this from memory. V1 over R plus j omega L, or what I called ZL, right? And then I have a term with V2 in it that is multiplied by 1 over R plus 1 over R plus ZC. And that is equal to IS, which we said was 2 with an angle of 0. So what I do is I say, all right, I'm going to create a matrix that is 1, 1 for the top equation. And on the bottom, 1 over R plus ZL and 1 over R plus 1 over R plus ZC.
Shouldn't it be a -1 up top?
Oh yeah, it should be a -1. Yeah, thank you. Right. That times V1, V2 equals VS, IS. Okay. That can be put into MATLAB right away, right? I don't want to start doing augmented matrices. I have complex numbers now, right? This guy's nasty, but I can put this all into MATLAB, and that's what I would do, and that is what I did. Okay, I take those numbers there, and I put that stuff into MATLAB, like I said. Okay, and if you go through, I'll give you guys this. If you look at this, right, and go through it, you're gonna get the answer here, which is to say, I'm gonna solve. So what I do down here, just like I did before, here's where I solve for the node voltages right here, right? I solve for the node voltages here. Those are gonna be complex now, right? Because I'm doing with phasors. And so V has, I say abs to get the magnitude. I say angle, and I multiply by 180 over pi to get it in degrees. So that says that V1 in the time domain is that, and V2 in the time domain is that. Okay, same frequency, but different phases and different amplitudes, right? That's the basic idea. So we did a lot there pretty quickly, right? But the important takeaway for us is nothing wrong with everything I've done before. I can get all the matrices and stuff, it's just all complex now, right? That's the only real difference that seems to apply in this particular case, okay? One thing that'll confuse you as we start going through some of these problems is the capacitor impedance will often be shown to be negative, right? I say 1 over j omega c, but 1 over j omega c, remember, is the same as negative j over omega c. That'll confuse you, and that will screw up your equations a lot. All right, so just be wary of that as we go through. We got lots more to talk about. All right, but the next homework 5, is all about this stuff. Right, so it's time to dig in. Okay. All right, I'm going to stop my recording there.